Welcome aboard, fellow enthusiasts, as we embark on another incredible video. Hello, dear viewers. Get ready to expand your horizons as we delve into Bremsstrahlung. In particle physics, is electromagnetic radiation produced by the deceleration of a charged particle when deflected by another charged particle, typically an electron by an atomic nucleus. The moving particle loses kinetic energy, which is converted into radiation, i.e. photons, thus satisfying the law of conservation of energy. The term is also used to refer to the process of producing the radiation. Has a continuous spectrum, which becomes more intense and whose peak intensity shifts toward higher frequencies as the change of the energy of the decelerated particles increases. Broadly speaking, or breaking radiation is any radiation produced due to the acceleration positive or negative of a charged particle, which includes synchrotron radiation, i.e. photon emission by a relativistic particle, cyclotron radiation, i.e. photon emission by a non-relativistic particle, and the emission of electrons and positrons during beta decay. However, the term is frequently used in the more narrow sense of radiation from electrons from whatever source slowing in matter. Bremsstrahlung emitted from plasma is sometimes referred to as free radiation. This refers to the fact that the radiation in this case is created by electrons that are free, i.e. not in an atomic or molecular bound state before, and remain free after, the emission of a photon. In the same parlance, bound radiation refers to discrete spectral lines an electron jumps between two bound states, while free-bound radiation refers to the radiative combination process, in which a free electron recombines with an ion. Prepare yourself for an eye-opening discussion on classical description in the upcoming portion of this video. If quantum effects are negligible, an accelerating charged particle radiates power as described by the Lama formula and its relativistic generalization. As we progress through this video, let's now turn our gaze towards total radiated power. The total radiated power is P alpha frac gamma P bar epsilon 0 C left dot beta alpha frac left bold symbol beta kit bold symbol beta right a beta right where a bold symbol beta alpha frac math the velocity of the particle divided by the speed of light gamma equal assert a beta is the Lorentz factor is the vacuum permittivity dot bold symbol beta signifies a time derivative of and is the charge of the particle. In the case where velocity is parallel to acceleration, i.e. linear motion, the expression reduces to P opal V alpha frac gamma P var epsilon 0 where V is the acceleration. For the case of acceleration perpendicular to the velocity a bold symbol beta kit bold symbol beta equal, for example in synchrotrons, the total power is P op V alpha frac gamma P var epsilon 0. How radiated in the two limiting cases is proportional to of or of. Since EM, we see that for particles with the same energy east the total radiated power goes as M4 or M6, which accounts for why electrons lose energy to Bremsstrahlung radiation much more rapidly than heavier charged particles, e.g. muons, protons, alpha particles. This is the reason active energy electron-positron collider such as the proposed International Linear Collider cannot use a circular tunnel requiring constant acceleration, while a proton-proton collider such as the Large Hadron Collider can utilize a circular tunnel. The electrons lose energy due to Bremsstrahlung at a rate mE times higher than protons do. Let's now turn our attention to angular distribution and uncover the fascinating insights it brings to the table. The most general formula for radiated power as a function of angle is a frac p omega a frac pi var epsilon 0 frac left hatamoth n times left hatamoth n a bold symbol beta right times at bold symbol beta right left shatamoth dot bold symbol beta right where shatamoth n is a unit vector pointing from the particle towards the observer and is an infinitesimal bit of solid angle. In the case where velocity is parallel to acceleration, for example, linear motion, this simplifies to alpha frac opal v omega alpha frac pi var epsilon 0 frac sin theta a beta cos theta where is the angle between and the direction of observation shatamoth n. Let's now turn our attention to simplified quantum mechanical description and examine its role within the larger context. The full quantum mechanical treatment of Bremsstrahlung is very involved. The vacuum case of the interaction of one electron, one ion, and one photon, using the pure Coulomb potential, has an exact solution that was probably first published by A. Sommerfeld in 1931. This analytical solution involves complicated mathematics, and several numerical calculations have been published, such as by Karsas and Latter. Other approximate formulas have been presented, such as in recent work by Weinberg and Pradler and Semelrock. This section gives a quantum mechanical analog of the prior section, but with some simplifications to illustrate the important physics. We give a non-relativistic treatment of the special case of an electron of mass me, charge E, and initial speed v decelerating in the Coulomb field of a gas of heavy ions of charge Z and number density Ni. The emitted radiation is a photon of frequency and energy. We wish to find the emissivity J, which is the power emitted per solid angle in photon velocity space photon frequency, summed over both transverse photon polarizations. We express it as an approximate classical result times the free emission Gaunt factor G for counting for quantum and other corrections. Ij of nu equal pi over cert left over pi epsilon, a right is an I over kmv for vernuj, v0 if that is, the electron does not have enough kinetic energy to emit the photon. A general, quantum mechanical formula for GM exists but is very complicated, and usually is found by numerical calculations. We present some approximate results with the following additional assumptions of a Coulomb interaction. We neglect any effects of the background medium, such as plasma screening effects. This is reasonable for photon frequency much greater than the plasma frequency nu p proto n ea with Ne the plasma electron density. Note that light waves are evanescent from a nu p and a significantly different approach would be needed. Soft photons, MeV, that is, the photon energy is much less than the initial electron kinetic energy. With these assumptions, two unitless parameters characterize the process, ZZ, which measures the strength of the electron-ion Coulomb interaction, and MeV, which measures the photon softness and we assume is always small. The choice of the factor 2 is for later convenience. In the limit Z1, the quantum mechanical Born approximation gives G at xven equals SR2 over Pilm over E to nu. In the opposite limit Z1, the full quantum mechanical result reduces to the purely classical result G at xv class equals SR2 over P left where 0.577 is the Euler-Mascherny constant. Note that's MeV which is a purely classical expression without Planck's constant h. A semi-classical, heuristic way to understand the Gaunt factor is to write it as G flane B max min, where B max and B min are maximum and minimum impact parameters for the electron-ion collision in the presence of the photon electric field. With our assumptions, B max over nu for larger impact parameters, the sinusoidal oscillation of the photon field provides phase mixing that strongly reduces the interaction. Bm-min is the larger of the quantum mechanical de Broglie wavelength Hem-ev and the classical distance of closest approach Em-ev where the electron-ion Coulomb potential energy is comparable to the electron's initial kinetic energy. The above approximations generally apply as long as the argument of the logarithm is large, and break down when it is less than unity. Namely, these forms for the Gaunt factor become negative, which is unphysical. A rough approximation to the full calculations, with the appropriate Born and classical limits, is G at text for proximax left right. As we transition to the next segment, let's unravel the mysteries surrounding thermal Bremsstrahlung, emission and absorption and gain a fresh perspective. This section discusses Bremsstrahlung emission and the inverse absorption process called inverse Bremsstrahlung in a macroscopic medium. We start with the equation of radiative transfer, which applies to general processes and not just Bremsstrahlung. A frac partial T I nu Schatmeth Ditnibler I nu equal J nu K nu I nu. Iert, X is the radiation spectral intensity, or power per area photon frequency summed over both polarizations. J is the emissivity, analogous to Jov, I defined above, and K is the absorptivity. J and K are properties of the matter, not the radiation, and account for all the particles in the medium, not just a pair of one electron and one ion as in the prior section. If I is uniform in space and time, then the left-hand side of the transfer equation is 0, and we find I nu over K nu. If the matter and radiation are also in thermal equilibrium at some temperature, then I must be the black-body spectrum. B nu te al frac nu frac I nuke text e. Since J and K are independent of I, this means that J must be the black-body spectrum whenever the matter is in equilibrium at some temperature regardless of the state of the radiation. This allows us to immediately know both J and K once one is known for matter in equilibrium. The time has come to unravel the secrets behind in plasma and gain a deeper understanding. NOTE, this section currently gives formulas that apply in the Rayleigh limit K and does not use a quantized Planck treatment of radiation. Thus a usual factor like Ix bar megok does not appear. The appearance of E in Y below is due to the quantum mechanical treatment of collisions. In a plasma, the free electrons continually collide with the ions, producing Bremsstrahlung. A complete analysis requires accounting for both binary Coulomb collisions as well as collective dielectric behavior. A detailed treatment is given by Beckfy, while a simplified one is given by Ikimaro. In this section we follow Beckfy's dielectric treatment, with collisions included approximately via the cutoff wave number. Consider a uniform plasma with thermal electrons distributed according to the Maxwell-Boltzmann distribution with the temperature Te. Following Beckfy, the power spectral density power per angular frequency interval per volume, integrated over the whole senior of solid angle, and in both polarizations of the Bremsstrahlung radiated, is calculated to be a marfm brova du megal frac cert a per left I over m e ker left z I n e over k bt I where p n e is the electron plasma frequency, is the photon frequency, n I is the number density of electrons and ions, and other symbols are physical constants. The second bracketed factor is the index of refraction of a light wave in a plasma, and shows that emission is greatly suppressed for omega p. This is the cutoff condition for a light wave in a plasma. In this case the light wave is evanescent. This formula thus only applies for omega p. This formula should be summed over ion species in a multi-species plasma. The special function E is defined in the exponential integral article, and the unitless quantity y is y frac omega me over k at x max k at x t. K max is a maximum or cutoff wave number arising due to binary collisions, and can vary with ion species. Roughly, K max be when K is EIH typical in plasmas that are not too cold, where EH 27.2 eV is the Hartree energy, and BM is the electron thermal de Broglie wavelength. Otherwise, K max LC where LC is the classical Coulomb distance of closest approach. For the usual case KMB, we find Y alpha left. The formula for but is approximate, in that it neglects enhanced emission occurring for slightly above. In the limit y1, we can approximate E as Elaine I where 0.577 is the Euler-Mascheroni constant. The leading logarithmic term is frequently used, and resembles the Coulomb logarithm that occurs in other collisional plasma calculations. For YE the log term is negative, and the approximation is clearly inadequate. Beckfy gives corrected expressions for the logarithmic term that match detailed binary collision calculations. The total emission power density, integrated over all frequencies, is a beginnerline p amarthamba I into omega at x pinthi du mega frac amarthamba du mega al frac left frac xi nik at x max g at x gp a frac certa pi and y at x pinthi d y a left e I y at x I omega at x penduline. dp01 and decreases with yp, it is always positive. For k max b, we find p amarthamba equal I over a left frac e a p ver epsilon a right over m e k frac bar z I n e k bt e frac d p. Note the appearance of due to the quantum nature of lambda b. In practical units, a commonly used version of this formula for G1 is Here mathb equals ZININE over left T a frac. This formula is 1.59 times the one given above, with the difference due to details of binary collisions. Such ambiguity is often expressed by introducing quant factor GMB, e.g. in one finds a epsilon itx equal a times frac n en is g itx, where everything is expressed in the CGS units. Let's now shift our focus to relativistic corrections and explore the ways in which it shapes our perspective. For very high temperatures, there are relativistic corrections to this formula, that is, additional terms of the order of. Get ready for an enlightening exploration as we dig into Bremsstrahlung cooling and understand its role in the broader context. If the plasma is optically thin, the Bremsstrahlung radiation leaves the plasma, carrying part of the internal plasma energy. This effect is known as the Bremsstrahlung cooling. It is a type of radiative cooling. The energy carried away by Bremsstrahlung is called Bremsstrahlung losses and represents a type of radiative losses. One generally uses the term Bremsstrahlung losses in the context when the plasma cooling is undesired, as e.g. in fusion plasmas. Moving on to the next segment, we have polarizational Bremsstrahlung. Polarizational Bremsstrahlung, sometimes referred to as atomic Bremsstrahlung, is the radiation emitted by the target's atomic electrons as the target atom is polarized by the Coulomb field of the incident charged particle. Polarizational Bremsstrahlung contributions to the total Bremsstrahlung spectrum have been observed in experiments involving relatively massive incident particles, resonance processes, and free atoms. However, there is still some debate as to whether or not there are significant polarizational Bremsstrahlung contributions in experiments involving fast electrons incident on solid targets. It is worth noting that the term polarizational is not meant to imply that the emitted Bremsstrahlung is polarized. Also, the angular distribution of polarizational Bremsstrahlung is theoretically quite different than ordinary Bremsstrahlung. Now, let's redirect our focus towards X-ray tube and discover its significance in our narrative. In an X-ray tube, electrons are accelerated in a vacuum by an electric field towards a piece of metal called the target. X-rays are emitted as the electrons slow down decelerate in the metal. The output spectrum consists of a continuous spectrum of X-rays with additional sharp peaks at certain energies. The continuous spectrum is due to Bremsstrahlung, while the sharp peaks are characteristic X-rays associated with the atoms in the target. For this reason, Bremsstrahlung in this context is also called continuous X-rays. The shape of this continuum spectrum is approximately described by Kramer's law. The formula for Kramer's law is usually given as the distribution of intensity photon count I against the wavelength of the emitted radiation, lambda equal to frac lambda min a right frac lambda. The constant is proportional to the atomic number of the target element, and min is the minimum wavelength given by the Dunhunt law. The spectrum has a sharp cutoff at which is due to the limited energy of the incoming electrons. For example, if an electron in the tube is accelerated through 60 keV, then it will acquire a kinetic energy of 60 keV. And when it strikes the target, it can create X-rays with energy of at most 60 keV by conservation of energy. This upper limit corresponds to the electron coming to a stop by emitting just one X-ray photon. Usually the electron emits many photons, and each has an energy less than 60 keV. A photon with energy of at most 60 keV has wavelength of at least 21, so the continuous X-ray spectrum has exactly that cutoff, as seen in the graph. More generally, the formula for the low wavelength cutoff, the Dunhunt law, is lambda min a frac the prox a frac of a mathma, where is Planck's constant, is the speed of light, is the voltage that the electrons are accelerated through, is the elementary charge, and is picometries. Now, let's shift our perspective and explore beta decay through a fresh lens, unlocking new perspectives. Beta particle emitting substances sometimes exhibit a weak radiation with continuous spectrum that is due to Bremsstrahlung. See the outer Bremsstrahlung below. In this context, Bremsstrahlung is a type of secondary radiation, in that it is produced as a result of stopping or slowing the primary radiation beta particles. It is very similar to X-rays produced by bombarding metal targets with electrons in X-ray generators as above, except that it is produced by high-speed electrons from beta radiation. Get ready to immerse yourself in the world of inner and outer Bremsstrahlung as we examine its impact and relevance. The inner Bremsstrahlung, also known as internal Bremsstrahlung, arises from the creation of the electron and its loss of energy due to the strong electric field in the region of the nucleus undergoing decay as it leaves the nucleus. Such radiation is a feature of beta decay in nuclei, but it is occasionally less commonly seen in the beta decay of free neutrons to protons, where it is created as the beta electron leaves the proton. In electron and positron emission by beta decay, the photon's energy comes from the electron-nucleon pair, with the spectrum of the Bremsstrahlung decreasing continuously with increasing energy of the beta particle. In electron capture, the energy comes at the expense of the neutrino, and the spectrum is greatest at about 1/3 of the normal neutrino energy, decreasing to zero electromagnetic energy at normal neutrino energy. Note that in the case of electron capture, Bremsstrahlung is emitted even though no charged particle is emitted. Instead, the Bremsstrahlung radiation may be thought of as being created as the captured electron is accelerated toward being absorbed. Such radiation may be at frequencies that are the same as soft gamma radiation, but it exhibits none of the sharp spectral lines of gamma decay, and thus is not technically gamma radiation. The internal process is to be contrasted with the outer Bremsstrahlung due to the impingement on the nucleus of electrons coming from the outside, i.e., emitted by another nucleus, as discussed above. Now, let's dig deeper into radiation safety and unveil the hidden treasures it holds within. In some cases, such as the decay of the Bremsstrahlung produced by shielding the beta radiation with the normally used dense materials, e.g. lead, is itself dangerous. In such cases, shielding must be accomplished with low-density materials, such as plexiglass, lucite, plastic, wood, or water. As the atomic number is lower for these materials, the intensity of Bremsstrahlung is significantly reduced, but a larger thickness of shielding is required to stop the electron's beta radiation. Get ready for a thought-provoking discussion as we delve into astrophysics and its impact on our understanding. The dominant luminous component in a cluster of galaxies is the 2 Kelvin intracluster medium. The emission from the intracluster medium is characterized by thermal Bremsstrahlung. This radiation is in the energy range of X-rays and can be easily observed with space-based telescopes such as Chandra X-ray Observatory, XMM Newton, ROSAT, ASCA, EXOSAT, Suzaku, RHESSI, and future missions like IXO-1 and Astro H2. Bremsstrahlung is also the dominant emission mechanism for HII regions at radio wavelengths. Let's now turn our gaze towards electric discharges and explore the fascinating connections it has to offer. In electric discharges, for example as laboratory discharges between 2 electrodes or as lightning discharges between cloud and ground or within clouds, electrons produce Bremsstrahlung photons while scattering off air molecules. These photons become manifest in terrestrial gamma-ray flashes and are the source for beams of electrons, positrons, neutrons, and protons. The appearance of Bremsstrahlung photons also influences the propagation and morphology of discharges in nitrogen-oxygen mixtures with low percentages of oxygen. As we progress through this video, let's shift our attention towards quantum mechanical description and uncover its hidden depths. The complete quantum mechanical description was first performed by Bethe and Heitler. They assumed plane waves for electrons which scatter at the nucleus of an atom, and derived a cross-section which relates the complete geometry of that process to the frequency of the emitted photon. The quadruply differential cross-section, which shows a quantum mechanical symmetry to pair production, is Beginnerline der Sigma a frax alpha x 5 bar a pi a frac left mask ferrite I left mask I diffract omega omega frac omega I do omega f duff I left mask ferrite a times left and lean was is the atomic number. Find the fine structure constant, the reduced Planck's constant, and see the speed of light. The kinetic energy E kin, if of the electron in the initial and final state is connected to its total energy EI, F, or its momenta pi, F via EI, F equal E at X kin, if plus m equals certum E chem off pi, where m E is the mass of an electron. Conservation of energy gives EF EI, where is the photon energy. The directions of the emitted photon and the scattered electron are given by a beginnerline theta I a spherical angle math theta f a spherical angle math phi a text angle between the planes a math text and a math enderline where k is the momentum of the photon. The differentials are given as a beginnerline do omega I a sin theta I do theta I do omega f a sin theta f do theta phi enderline. The absolute value of the virtual photon between the nucleus and electron is a beginnerline math and left math right left math phi left fract break omega right plus a left math right fract break omega cos theta I a left math phi fract break omega cos theta f and plus a left math right left math right left cos theta I a sin theta e cos of right enderline. The range of validity is given by the Born approximation of Obfrax, where this relation has to be fulfilled for the velocity v of the electron in the initial and final state. For practical applications, e.g. in Monte Carlo codes, it can be interesting to focus on the relation between the frequency of the emitted photon and the angle between this photon and the incident electron. And Ebert integrated the quadruped differential cross-section by Beth and Heitler over and F and obtained alfractor sigma e omega theta I do omega I are some limits ij. With a beginnerline I1 alfractor set delta plus ib ip first in theta I am left frac delta plus ib ip first in theta I set delta plus ib ip first in theta left delta 1 delta a right delta a delta ib ip first in theta I set delta plus ib ip first in theta left delta 1 delta a right delta and a times left I to a frac ip fifth I equals theta a right and left frac f plus p fp for right I 3 equal frac p assert left delta f delta 1 pf right plus pip first in the theta I a times left right a right a left right a left right a right and a left delta 1 delta a right left set left delta 2 ef delta 1 pf right plus pip first in the theta a right and a times left I 4 and a frac appear pf cliff delta 2 ef delta 1 pf right a left delta f delta 1 pf right plus pip first in the theta I frac pip a left delta f delta 1 pf right a left plus pip first in the theta a right I 5 a frac appear left delta 4 pip first in the theta a right left plus pip first in the theta a right and a times left I 6 and a frac up if pis in the theta I left I equals theta a right I left delta ip first in the theta a right enderline and beginnerline. I frac sulfur ticks fine a pi a frac left math phi tie f math right a frac by omega delta 1 a math I a math left frac brick omega right a frac brick omega left math I cos theta I delta 2 a frac brick omega left math right a left math right left math phi cos theta I. Enderline. However, a much simpler expression for the same integral can be found in IC. And in IC. For point 1. An analysis of the W differential cross-section above shows that electrons whose kinetic energy is larger than the rest energy 511 emit photons in forward direction, while electrons with a small energy emit photons isotropically. Let's now shift gears and explore electron Bremsstrahlung through a critical lens, uncovering its strengths and weaknesses. One mechanism considered important for small atomic numbers is the scattering of a free electron at the shell electrons of an atom or molecule. Since electron Bremsstrahlung is a function of Z and the usual electron nucleus Bremsstrahlung is a function of electron Bremsstrahlung is negligible for metals. For air, however, it plays an important role in the production of terrestrial gamma ray flashes. Remember, knowledge is power. Keep learning, growing, and exploring.